Welcome to this video on Pytorch. If you are new to Pytorch, this video would help you to write the first code using Pytorch. The objective of the session is we will create a simple multi-layered perceptron to train a regression model. And then after the model is trained, we will save the model and then we will see how to load the model which is already saved so that we can predict new values. In the subsequent videos, we will create models where we can use inbuilt data sets and custom data sets. First, let's see what problem we are trying to solve. The data set is the very famous data set which is used in the Christopher Bishop book, which is used for regression, typically called the polynomial curve fitting problem. I have a x, which is my input, and for which I'm trying to find the output, which is y. And the pattern in y is that it is following a sinusoidal curve, as shown in the right-hand side. To be more elaborate, the input is a fabricated data set with one input x and the output is y. The reason I call it as a fabricated data set is I already know the pattern that my y has to follow because I have fabricated my y in such a way that y is equal to sine of x. So this is my input and this is my output. And if I plot my x and the corresponding y, as I said, this is the pattern I'm expected to find. So the objective of the code is, given an x and a y, the model should be trained in such a way that it identifies the pattern, which is this pattern. To create the input x, I use a function called as linspace. Linspace basically has 3 parameters which are required, which is start, end, and steps, and 2 keyword arguments which are optional, which is the data type and the device. Linspace creates one tensor, which is a one-dimensional tensor, and the number of elements or the items in the tensor is given by steps, and the values which are found in this tensor are evenly spaced from the start value to the end value given, inclusive of both the start and the end values. Start is a floating point type. This is the starting value for the set of points that I'm trying to create. End is also a floating point type, which is the ending value. Steps determines the number of points that I want in my data. D type is the data type of the torch I'm expecting. Tensor which I'm going to use can either be working on a CPU or it can be working on a GPU. And as the case may be, I will give it as either CPU or CUDA. If I do not have a GPU system, I will use a CPU system and just put this device as CPU. So this is an example of the code which is written. I create a tensor called as x. I start from the value -5 and I end at 5. And I'm expecting 6 data points in between, all of data type float 32. And the device which I'm going to use is the CPU. Please note that by default, D type and the device, it would still consider the data type to be float 32 and the device to be a CPU because that's the default value for it. So as you can see, I have created a tensor here and the starting value is -5. They're all evenly spaced. If you look at the spacing between -5 and -3, same as the spacing between -3 and -1, which is the same as the spacing between -1 and 1. So basically, they're all evenly spaced with a difference of 2. And as we had already mentioned, starts with a -5 inclusive and ends with a 5 inclusive. This is the input that we have created. Now let's create the output. Now the output, we are fabricating it to be the sign of the input. The input should be a tensor for to create a sign value. I have created the tensor using torch.linspace, which is a tensor for the input. You might be wondering what is a tensor. In that case, if you know what an array is, I think right now we'll just go by the definition. You can just think of it as an array. So it's basically a one-dimensional array with 6 values that you have created. And why do I very specifically call it as a tensor? The operations have been optimized in such a way that even when they work on a GPU, their speed is much higher. Okay. We can understand it in that way in a simple fashion. So that's why I call X to be a tensor. So you can also think of it as just a one-dimensional array, which is computationally very good in a GPU. Okay. The next thing is the output Y, where Y is nothing but the input sign of the input, which is X. So we see that for the different values of X, the different values of Y that we get. Now, if we try to print the shape of the tensor, we print X dot shape. We see that it is one row with 6 columns. Since it is one dimensional, we have a list with just one scalar value 6. We will see how it changes when I have more than one dimension. So what happens here? I have created a tensor, and the tensor has one row and 6 columns, as shown in the shape also. But in reality, when you want to give it as input to a artificial neural network, like a multi-layered perceptron, we want to give different samples as input. Each should be a different row. So now, what I had it as one row with 6 columns should now become 6 rows with 1 column. To achieve that, I use something called as the reshape. Reshape takes an input tensor, and it also asks you to specify what should be the shape of the output tensor. So this is a tensor, whereas the shape is a tuple of integers. Let's see it with the help of a code. So I'm now using torch.reshape. I need to reshape X. So that's my input. Remember, Pytorch works only with tensors. X is already a tensor because we used torch.linshape. Torch.linshape by default creates a tensor. Similarly, torch.sign by default creates a tensor. So this X is by default a tensor. So my input, as I had already mentioned, is a tensor. Now I require the shape. The current shape that I have is one row with 6 columns. I am now going to convert it with 6 rows and 1 column. So I specify within a tuple. So this is a tuple there. I specify the integers 6 and 1. Now when I try to print the shape of samples, I get it as a tensor with 6 rows and 1 column. So here I have mentioned the number of rows and the number of columns. It is also possible for me to write in a slightly different manner where I need not specifically give the number of rows, but rather from the fact that I have 6 elements and I have specified that I need only 1 column, it will automatically assume that the number of rows I need is 6 if I just give a -1 in the place of 6. So this also creates the samples in the way that we require, that is 6 rows and 1 column. So right now I have 6 samples which I have to process. First, you need to import torch. And first, let me create the first data set. It is equal to torch.linspace. Let's say I require values from -3 to 3, and I require, let's say, 8 values. And if I do not mention the data type, it would take a float 32 by default, and the device would be a CUDA by default. And let me have a Y. The Y is the corresponding sign of the X that I have created. Now let me try and print X and Y. So when I run it, you can see that I have 8 values here and their corresponding sign values. I have not mentioned the data type of the values in X. Now let's try and print what should be the data type. So it is X dot D type. And let me have X dot device, because that is also something I have not specified. So as you can see, by default, it takes it as a tosh.float 32. And by default, the device which is required, which is considered as the CPU. Now let's reshape it. Let me reshape it with a xtrain. So that's a tosh.reshape. I need to reshape X. I want to convert it into a sample with 1 column. And then let me try and print xtrain. To create the neural network architecture, there are a couple of steps that we need to do to train a model. That is, we create the architecture, we go through the samples in the training data set one by one. And for every sample, we calculate the output by a forward pass. Then we find the loss. Then we backpropagate the loss and we update the weights and the bias. In this particular example that we're going to do, we're going to consider a gradient descent, a normal gradient descent. So so we're not going to consider any batch sizes. So what are the steps to create an architecture in Pytorch? That is, I just want to create the input and the output layers and the hidden layer. So first, I have to create a class. So this class is the representation of the neural network architecture. In my example, I have given the name of my class to be simple ANN. This has to inherit tosh.nn.module. We have to initialize the layers in the architecture in the constructor. And then we implement the forward pass in a function called as forward. So in the rest of the session, we are going to look at how to write this init and how to write the forward and actually do a full-fledged training. First, let's initialize the layers. So to initialize the layers, I will require 3 layers as shown here. X is the input layer. This is my hidden layer. And this is my output layer. But when you look at it in terms of MLP, generally we say only the hidden layer to be the first layer and the output layer to be the second layer. We ignore calling the input layer as a layer. So I have a 2-layered architecture here with 1 hidden layer and 1 output layer. Now the first part, which is from X, which is the input layer to the hidden layer, is specified by this tosh.nn.linear, wherein I have to specify the number of nodes in the layer. The number of nodes in the layer is given as 5. So I'm going to create a hidden layer with 5 nodes. This takes input from the input layer, and in the input layer, I have only 1 node. So I have given that it is a linear layer with dimension 1, 5. That is one input going to 5 nodes in the hidden layer. And initially, I've just mentioned it as a linear layer. I have not said what activation function I need, which can always be added later. Now, the second layer that I have to mention is the output layer, which is composed of only one node. So it is a 1 in the second as the second value, but it takes input from 5 different nodes in the hidden layer. So it is a linear layer of 5, 1. That is, there are 5 nodes in the hidden layer going to 1 node in the output layer. Now let's see how the forward pass is done. Initially, I have to pass in forward the self object and the input, which is X. So when I pass X, from which layer to which layer it has to move to is given only in the forward pass. Remember, in the constructor, I only said what are the different layers and what is the dimension of each layer. I have not said from which layer the input goes to which layer. I have not mentioned the flow of data. The flow of data is mentioned only in the forward pass. So here, for example, if you see def forward self of X, so I start from X. Now this input is given to this layer, self.hiddenL, the output of which I call it as L1. So far, it's like this. So the output of this layer after a linear activation is L1. I pass it through the ReLU activation function and I get the output as H1. This H1 is given as input to the output layer. And then the output from the output layer is taken as L2. And that is the final value that I will get after making a forward pass. So let's look at it in detail, what happens internally during a forward pass. So now, first I say that I have a X, which is going as input to the first layer. So when it goes as input to the first layer, I calculate L1, which is W1 into X plus B1. And for the second hidden node, I calculate L2, which is W2 into X plus B2, and so on till the fifth hidden node, which is W5 into X plus B5. Please note, this is what I've been calling so far as a linear activation because I've not added any activation, nonlinear activation function here. It is just the net input. We call it as the net input because it combines the weight, the input, and the bias. Subsequently, what happens is I calculate this for all the samples, and so the L1 is now a tensor which has 5 columns, where the 5 columns will represent the values from the 5 hidden nodes L1, L2, L3, L4, L5. Like this, I have for 2000 samples. So it is a 2000 cross 5. This output is then passed through an activation function in H1, which is a ReLU activation function. So this ReLU activation function, I take it from torch, which is torch.ReLU, and I pass that tensor for which I need to calculate the ReLU. So now I pass a tensor of 2000 cross 5 and I calculate the ReLU. I pass it through a ReLU activation function and I get the output. And this is represented by H1, H2, etc. up to H5. Then I need to calculate the forward pass from the hidden layer to the output layer. So for that, I call the net input to the output layer as L2, and I take it as W6 into H1, which is the output of node H1, W7 into H2, and so on. And I also need to add the bias in the output node, which is B6. So L2 is now a linear combination of W6, W7, etc., the output of the hidden nodes and the bias. This is the final output after a single forward pass, which is given as L2. And this is what you call as the predicted value. I had already, as I had mentioned in the slide, O I have taken as the predicted value because I've already used Y to represent the actual value. So after making a forward pass, the value that I get as output, which is L2, is now the predicted value. I have completed the first step, which is to create a neural network architecture. The second step is to specify what loss function I would like to use. Here I'm going to use an MSE loss, and reduction mentions what type of reduction I want. That is, I want to calculate the mean of all the loss of the 2000 samples, or I can find the loss for all the 2000 samples and sum it up, or I can leave them as it is. For example, in the first case, if it is a none, I would just take the loss, which is an MSE loss, which is the difference between yi and oi. Yi is the actual value, oi is the predicted value. I take the difference between them and square it. That is just a normal squared error loss. So there is no reduction there. If I want the summation of all the values, then it is sum. The reduction has to be specified as sum. By default, the reduction is a mean. So the next step is to create the optimizer. So what have I done so far? I have created the architecture. I have specified how the forward pass should take place. I have specified what loss function I want at the end. Now I need to specify what optimizer I need. So to specify the optimizer, I have taken a simple optimizer, which is your SGD, stochastic gradient descent. You pass two parameters for sure. One is you need to specify what are the parameters you want to update. And the second is what is the learning rate that you expect. So as can be seen in the program that I've written, the parameter that I want to update can just be given as model.parameters, where model is the object of simple ANN. We will see this while writing a code. I have specified the loss function as an object. I have constructed the optimizer object by specifying optimizer is equal to torch.optim.sgd. Then I need to make the actual forward pass. To make the actual forward pass, I need to have the object of the simple ANN and pass the data set. This is a Python code, and so you can just call model. Model is basically an instance, but you can just call it like a function if it has the __call__ function written in it. And since we have already inherited it from torch.nn.module, this is already present in the inherited class. Here, model would in turn call the call function with the parameter xtrain, and this call function would in turn call the forward function. When I write the statement mod output is equal to model of xtrain, automatically the forward pass takes place. So during the forward pass, first it calculates the net input, as I said, in the linear layer, and then we pass it through a ReLU. So as can be seen, all the negative values have become a 0. So the output of this hidden node is now this value which is given here after passing it through a ReLU activation function. What will be the output of the output node? It has to be L2. And as we can see this now predicts this value after passing it through a normal linear layer. Remember, for this particular problem, we have not used any activation function in the last layer. So we have performed the first 4. Now we need to calculate the loss between the predicted and the actual values. So for that, again, we call the instance of the loss like a function, and we pass the predicted value and the actual value. This calculates the loss function using the formula which is shown. Here we have used a normal gradient descent, and so the batch size is 2000, based on which it calculates the loss. And the output is shown. I have created the architecture. I have said what loss function I want. I have said what optimizer I want. I have made a forward pass. I have calculated the loss after making a forward pass. Now I need to back propagate the loss. The loss is back propagated using loss.backward. It calculates the gradients for all the parameters that are there. What are the parameters in our model? The parameters are the weights and the bias. So loss.backward would actually calculate the gradient for all the parameters or the weights and the bias in the model. So if you look at it, the weight of the hidden layers and the bias in the hidden layers, before and after loss.back propagation, the values of the weights and the bias will be the same, because loss.backward only calculates the gradient. It does not touch the values of the weight and the bias. Whereas if we try to see the gradient before giving the function loss.backward, this is the gradient that we have. But after giving the function loss.backward, this is the gradient that we achieve. So loss.backward only computes the gradient and updates the gradient in every node that is found in the network. Let's also look at what happens in the output layer. If you look at it, before back propagation and after back propagation, the weights and the bias remain the same. As if you look at the gradient, it has changed before back propagation and after back propagation. In other words, loss.backward finds the gradient and updates all the gradients for the different parameters in the model. Now that we have updated or calculated the gradient of all the parameters of all the nodes in the architecture, we now need to update the weights. Now to update the weight, we make use of optimizer.step. Now before and after the step function, the gradient, if you look at it, it remains the same. There is no change in the gradient. We do not touch the gradient at all. But the weight before optimizer was .step is as shown in the first picture. Whereas after optimizer.step, we see that the weights and the bias have changed. That is, they have been updated with respect to the gradient that was already calculated. So optimizer.step updates only the weights. This we can see in the output layer also, where we see that the gradient remains the same before and after optimizer.step. But if you look at the weights, they have changed. That is, the weights have been updated. Now let's try to really train a model. So the data set is insufficient. Let's have at least 2000 values for our model to be able to understand what it is. So first, let me create the architecture. So class simple ANN. I have to import torch.nn.module. Let me create the constructor. And I need to call the constructor of the base class. Now I need to create my layers. So I can create one layer as self.l1 is equal to torch.nn. Torch.nn is the package that has all the classes required to create the different layers. And linear is the name of the class used to create a linear layer. So torch.nn.linear. I have only one input, but I want 5 nodes in the hidden layer. And then I want another layer. Let me call it as L2. And that also I want it as a linear layer that has 5 nodes to 1 output node. Now let me define the forward function in which I require the input, which is X. This is where I specify how I want the inputs to be, how I want the data to flow. So let me first start from the first one. So first let's start from D1. It flows from self dot L1 is the first layer I want, to which I want to pass X. Now the output of the linear net input in the hidden layer is now D1. I want to pass it through a relu. So let it be a torch.relu. These are all functions which are found in the torch function. All the activation functions are found there. And for that, I give the value D1 as input. And now I have the relu. Let me pass the relu through the next layer, which is self.l2. And D2 is passed here. And then let me return D3. So I have just created the architecture here, and then it is here that I mention how the data flows. So even if you're going to put it as L2 first and L1 first, it's not going to matter at all, as long as the flow of data is correct in this. X2 L1, D1 goes to relu, D2 goes to the third layer, and D3 is the output of the third layer. So this is where the flow matters. Next, we create the instance for the class simple ANN. I can print the model, and as you can see, it prints the architecture of the simple ANN. So first I have to create an object for the loss function. So let me call it as criterion, and it is in the NN package, all the classes for the loss function. Let me take MSC loss. I hope I'm right. So MSC loss. And I am not specifying the reduction because by default, as we have seen, it takes a mean, and I'm fine with that. Similarly, I need the optimizer. Optimizer, I have to create an object for torch. It's found in torch.optim. All the optimizers are found in torch.optim, and let me use SGD. Register all the parameters. So the parameters are the parameters in model. So here all the parameter in model is what I'm interested in. And the learning rate, I have it as 10e minus 2. So these are the two things I require. I create the object for the loss function, which is in torch.nn, and the object for the optimizer, which is in torch.optim. It should have been model.parameters. So let me also decide on the number of epochs. Let me have 100 epochs. So let me start with one epoch first and then move on. Now I have to run it for all the epochs. So let me start with 2 epochs and say for epoch in range of epochs. So it first takes 1, then 2. We have seen that the gradient has to be calculated at every node. Pytorch by default will accumulate all the gradients. Every time we want to make a backward propagation or a back propagation, we want the gradients to remain at 0. We do not want the gradients to add to the gradients that was already calculated in the previous back propagation. So to ensure that during every back propagation, a new gradient value is calculated and used in the weight updation, I have to write optimizer.0 underscore grad. This ensures that all the gradients are 0 when I start every epoch. Now first let me make the forward pass. So I want the output. Output is equal to, we've already seen that when I call model with the input data, which is my X train, it automatically calls the forward function. This is something we've already seen. Now that the forward pass has been made, I now have my predicted value in output. Now let me calculate the loss between the predicted value, which is output, and the actual value, which is in Y train. Now that I have calculated the loss between the predicted and the actual values, I have to now make a back propagation. And this back propagation is made by loss dot backwards. Once I make a back propagation, as we've already seen in the presentation, this is going to calculate the gradients for all the parameters and store it there. Now that I have all the gradients, I need to make a updation of the weight, for which I use optimizer.step. And now the weights have been updated. Now let me try and print the loss. I can print the loss, and if I want only the loss, I can also print loss dot item. Now let me run it. Just that I had an extra S. It should have been loss dot backward. So I now have the loss. So if I run this, I get the loss for the 2 epochs as so on. So what I have done so far is I have calculated the loss, I have backpropagated, and I have updated the weights, and this I have done for 2 epochs. And I have a very reasonable loss of 0.75 and 0.709. It would be very helpful for us if we can find the values of the parameters, which is, let me try and print for model. There are 2 layers. One layer I have called it as L1, and the second layer I've called it at L2. Now L1 has a weight and a bias, and L2 also has weights and bias. Now let me try and print the weights. So that will be L1 dot weight. So I have the weight for that particular layer. It is printed twice because I gave the epoch as 2. Let me make this as 1 so that it's easier for us. So I'm able to print the weight in this way. I can also print the gradient of the weight parameter. As you can see, initially the gradient value is 0 as given here. Now let me try and print the weight after loss dot backward. What do we expect? The weight shouldn't have changed, but the gradient should have changed. So let's try and run this. So as you see, the weight has not changed, but the gradient has changed. Now after optimizer.step, what should have happened? I should have changed the weight also, but the gradient shouldn't change. Now let's try and run it. So as you see, between these, the weights have changed, but the gradient has not changed. Similarly, I can also try and print for the bias using model.bias, and model.bias models L1 layers bias. Similarly, I can do model.L2, which is taking the second layer and finding the bias, and I can find the gradient of that. So I can decide which layer I need, I can decide which parameter I need, and whether I need just the value or the gradient. So like this, I can display and check how the weights and the gradients are differing. Now, I am more worried about the training. So let me just avoid all the printf statements, which are going to take up most of my output space. Let me run this for 100 epochs, or let's say even 1000 epochs. Let me find the loss for every 100 epochs. So this 100 is equal to 0. And let me print it. F for, let me print the epoch number. And also the loss. So I have the loss at every epoch. We can save the model as a pickle file. And so we take the object, which is the architecture or the model of the neural network, pass that as the first parameter, and that is the object to be saved. And as the second parameter, we make use of the file path. This internally just calls the pickle module in Python. And this helps the object to be saved in that file path. And remember, when we write a Pytorch code and we want to save the model, one of the acceptable file extensions is a .pt. If I have a model already stored, I can load it using torch.load. I just need to specify the file path. To perform inferencing, we have to first convert it into an evaluate mode. When you convert it into an evaluate mode, you will learn later that there are certain layers called dropout and batch normalization, which are not required during testing, but are required during training. So when you convert it into the model.eval mode, it ensures that those layers that are not required during inferencing are not used. So it is always a good practice to use model.eval before trying to predict. So then if you want to predict the values for all the values in a tensor, I can just give model of and the name of the tensor. And if I want a particular value, I can just convert that particular value into a tensor and try to predict the value. So this is the final requirement for prediction. Let me first save the file using torch.save. I have to specify the object which I want to save, which is model, and the name of the file, which is, let's say I want it to be saved as model.pt. Since I have not given the path, it would be saving it in the current working directory. If I want to use this model, let me get the model from using torch.load, and what I want to load is model1.pt. If you have stored it at a different location, you will have to give the absolute path or the full path name. I have loaded it. After loading it, I can use it for evaluation purpose, and then I can predict the values using model. And let me predict the value for x train of 1. And let me print it and see. So I have now printed the value which was predicted for y x train of 1. Let it using a matplotlib. So these are the true predictions that is we are expecting, but the output after passing through the model is like this. We can make a lot of modifications here. We can increase the number of hidden layers. Now let's try and see how to increase the number of hidden layers and the number of nodes in the hidden layer. So we come to the simple ANN. Let's assume I have another hidden layer. So this will be, let's say, the first hidden layer has 10 nodes. And in between, I have another hidden layer. It takes these 10 nodes as input and goes through another 10 nodes. And the last node has to take from this. So D1 takes from X. D2 takes from L2. Let me use another torch.relu for D3. D3 is still the output of the second hidden layer. Now I am passing the output of the second hidden layer to D5, which will be nothing but a self dot L3, to which I pass L4. And so finally I need an L5. Now let me run all the cells below and see how it has smoothened even further. See, you can keep increasing the number of layers and the number of nodes in each layer to improve the quality of your model. So thank you. I assume you now know how to create a model using Pytorch and how to save the model, predict the model, and load the model. In the next series, we will see how to take an inbuilt data set, how to take custom data sets, and then do the same thing. The main objective of this video was to help you to know how to perform an entire training using Pytorch. But of course, the most difficult part would be to glean the data and to take it in the format which is required for the architecture, which we will see in the next video. Also, please note that the code is given in the links in GitHub.